Okay, good morning, everyone. Morning, everyone. How did your homework go? Okay. All right, Chris. So 45 and 57. And 57. All right. So let us first, before we do that, let us recall the. All right. Let us recall what idea we introduced yesterday. It was the notion of absolutely convergent, and the question is that if you have a series, we say that so it's A1 plus A2 plus etc. So it's absolutely convergent if when we take everything in absolute value, so we create a new series that consists of positive term alone, this one converge. That's what absolutely convergent is. Now, conditionally convergent, it means without absolute value, converge. With absolute value, diverge. So let's make it converge is that we have the pluses and minuses that make it converge. But when we start adding them up, the series will diverge. And then the main theorem, it tells me that if an absolute value converges, so then if we remove them, it will converge.
I have a question. What does that say in the corner where it says AK converge?
Right here?
A little bit down and to the left. To your left. It's yeah, I just can't see where it's what it says.
Conditionally convergent.
Oh, okay.
Okay, I didn't write it the whole thing because. All right. So this is the basic idea. Now we look at your problem, number 45. Are you done?
Yes.
So number 45. So we have the following series. Okay. Number 45, we have the following. Sigma minus 1 to the k over k to the power 0.99. 1 to infinity. And the question is the series absolutely convergent or converges or purely diverges? All right, so first we check the absolute value, because if it converges with absolute value, if it converges when we put absolute value, it will converge without them. So we're done. So first we check absolute conversion. All right. So we take sum of the absolute value of the term. $99. Okay. Sorry. We take sigma, absolute value of that. So an absolute value, what the absolute value will do is get rid of the negative. I will have sum of 1 over k to the power 0.99. K equal 1 to infinity. And now the question is the following: does the series converge or diverge? Back to you. It's not hard. Just look at it for a second. What type of series is that? Diverges by which series? Why? Okay, that's a P series with P equal 0.99, which is less than 1. Okay, so immediately diverges. So if we add those terms, we're gonna go all the way to infinity. All right, so it's not absolutely convergent. So in absolute value, it's not. So now the question is, what happened for the series by itself? So question number 2, let's look at the series itself. Does it converge or not? Okay, now without absolute value, does this series converge? What do you think? What type of series is that? Back to you. What type of series is this? Go ahead. What type of series is that? Means if I start to writing it up, what type of series I get? Exactly. Plus, remember, this is fixed. Plus 3 minus. Plus 1/4 and excess. So this is absolutely an alternating series. Okay. Now, does this converge? That's an alternating series. Does this converge? If both conditions of the alternating series test are satisfied, it will converge. So what are the terms? So the term in absolute value here are 1/k to the 0.99. So first, those terms, when k goes to infinity, this term goes to infinity. This will go to 0. First condition is satisfied. Second, those terms are decreasing because as k increases, the denominator increase means 1/decrease. So it's, again, that's an easy scenario of a decreasing sequence. So the sequence 1/k is decreasing. Okay, so the sequence is decreasing every term, because as the denominator, as k increases, the denominator is increasing. It means 1/it is absolutely decreasing. So by the alternating series test, since both conditions are satisfied, the series sigma -1 to the k over k converges. So conclusion. So what can we say about the series? Applying the absolute value, it diverges. I remove the absolute value, it converges. So what type of convergence do we call that? So conclusion, sigma, an absolute value, this one diverge. However, if we remove them, it converges. Because we're adding, we're subtracting, and condition of the divergence test is hence conditionally convergent. Convergent. Okay. Question, please, as I move on. All right, so let's look at the other question, which was number 57. Okay. Which I did not assign 57, Chris. Chris?
Let me see. That's what I wrote down. Let me see. Yeah, it was like 10.
57. 57, I don't think I assign it.
10.6.57.
No way.
I mean, that's just what it says on.
Yeah, if I did, I will remove it. I don't think I did. 57. What am I doing? Sorry, I'm in the wrong section. I apologize. I'm in the wrong section. Sorry. I'm totally in the wrong section. Whatever. Sorry, Chris. Yeah, you're right.
It's all right.
I'm looking at the wrong section. All right. Okay, this series. And the question is it converges absolutely, conditionally, or diverges? Yeah, I will look at it. All right. So look at this series immediately. Sometimes we have to start being very careful. If we look at this series, what can you say? Look at the terms.
It's gonna be infinity over infinity when you take the limit.
Gonna be what? Repeat.
It's gonna be infinity over infinity when you take the limit. Or
yeah, and it's gonna give you what?
It's not gonna be 0, so
Exactly,
it can't satisfy
exactly.
that one rule.
Then it's gonna diverge immediately. So this, from the beginning, it's gonna diverge. Let's watch very carefully those, because a lot of time you have to look at the terms. If I watch very carefully those, let us look at the limit as k goes to infinity of k over to k plus 1. So I look at this series and really immediately I look at those terms. So this is the limit. As k goes to infinity, we have infinity over infinity. This is 1 over 2 u sub beta is equal to 1/2, which is non-zero. So the terms, when k is large, the terms don't become small. Immediately, the series diverges by the divergence test. I'm done. Done. End of the problem. We don't go any further or whatsoever. So we are done totally with this problem. This series will diverge. The terms themselves don't get close to 0. All right, so I look at the other two problems quickly and then we proceed. So let's look at 50. What is it about? 50, I just did it a minute ago, Freddie. 50 is the problem I did. So this is 50. The problem I did is exactly the number 50 you're asking. It's minus 1 over k to the 0.99. So that's really number 50. Okay. All right. So now we look at problem number 61 and we move on. Okay, 61, we have the following. Sigma minus 1 to the k squared plus 1 over k to the power 3 minus 1, and k starting at 2 all the way to infinity. Very good. Again, so that's the series. What can we say about its conversions? First, if I try to imitate the previous one, and if I look at those terms, they will go to 0, because when k is large, this is almost k squared over k to the power 3 intuitively, which is 1 over k, which is go to 0. So I don't really have the divergence test. So this is useless in this scenario. So I have to look at it in first. I check the absolute value here because the question is absolutely or not. And I take everything in absolute value. It means sigma. When I take the absolute value, everything becoming positive right now. Okay. And now that's a new series. That's a series with positive terms. These are the term of the series. And the question is, does this new series with positive term only converge or diverge? So at this stage, we have to go back and use the test. So this is not a P series. No, it's not exactly a P series. So to check the conversions, I have to go through the test I know. Which test should I use? The integral test, the limit comparison test, or the regular comparison test? Which test do you think is the easier to check the conversions of this series? Back
Would
to
it
you.
be limit comparison?
Absolutely the limit comparison. Integral after question. Who want to integrate that? I don't, you don't. I mean, it's not, this one is not very hard, but it's just a mess here. So we don't want to handle that because integration is not very easy in this problem. Limit comparison is actually easy. Comparison is usually hard, as I said before, because you have to say it's less than or bigger than. It's not really very easy again in this scenario. Now, the limit comparison is simple because when I look at this series, so I'm going to call those AK. I say, okay, when K is large, my numerator acts like K squared. My denominator acts like K to the power 3. So the whole thing is 1 over K. So I'm going to compare it to the series sigma BK. Okay, so that's the limit comparison is the proper to do. Now I evaluate the ratio.
I have a question real quick.
Please go ahead.
So on that problem, I did the limit comparison test too.
Yes.
But as one of the answers, it doesn't give you the option. So like, what would be the next best, I guess is what I'm asking. Because it doesn't give you the option of saying that you did the limit comparison test, unless I'm reading it wrong.
I don't ask your question again because I don't think I.
But no, yeah, it's fine. So on the homework, it gives you like 5 options, like you did the comparison test or integral or whatever.
Okay, yeah.
And yeah, it doesn't give you the option of that unless I'm just reading it wrong. But
it doesn't give you the limit comparison?
No, I don't see it. That's why I had the question on it, because I did limit comparison, but it wasn't giving me the
best
option.
Yeah, the best one is the limit comparison. Now I can try the comparison test. Let's see if I can try. For me, yeah, the limit for me is the easiest. I don't know what I mean. Whatever they say, the limit is the easiest. I mean, it's just right there. It's just screaming at me, looking at me. Now, integral test is, I wouldn't advise it. I don't think they want integral test. This is not easy to integrate. Okay. So the only our choice we have is the regular comparison.
I think that's what I did.
The regular comparison. That's I would have done limit. I look at this. I don't really scratch my head too much. I look at it, limit comparison. This is my way, the way I go. That's how I will do it at the personal level. Now, the only thing it could, and I'm surprised they don't put the limit comparison into one of their choices. If when I use the comparison, we have to be very careful. We can probably use the comparison test, but this is going to diverge because based on this idea here, this is going to diverge. So if I need to use the limit, the comparison, it means I want this to be larger than something that diverge. I want it to be larger than something that diverge. So let's see how we can do it. K squared plus 1, the numerator is larger than K squared. Okay, am I right so far? Very good. Now this is K cubed minus 1. Now let's see. K to the power 3 minus 1 is basically less than K to the power 3. True or false? Are you agree with me? So when I flip it, this is going to be larger than K squared over K cubed, which is 1 over K. So the second would be the comparison test. It works. Okay. If I am doing it, as I said, I will go after the limit comparison. It's very easy for me. Zach, does this answer your question?
Yes, that does answer my question.
Yeah.
Thank you.
Yeah, so it's the comparison, and it works because comparison, you have to make sure 100% you can build the inequality. You cannot just say it is. K squared plus 1 is bigger than K squared. K cubed minus 1, so I kept it here. Now, K cubed is definitely minus 1 is less than K cubed, so when I flip it, it's going to be bigger than that, which is the 1 over K. So that's the other way you can do the problem. So in this case, if I take the limit here and I do all the math, I'm going to have K squared plus 1 over K to the power 3 times K over 1. Now, if I do this, I will get basically the limit of K cubed plus K over K cubed minus 1, which is equal to 1. Okay, so now L not 0, L is not infinity. Limit comparison test applicable. Now, since sigma 1 over K diverges, the series also will diverge. So sigma 1 over K diverges, the series K squared plus 1 over K cubed plus 1 also diverge. It means the series is not absolutely convergent. So again, that's another situation. So the original series is not absolutely convergent. So now I have to check it without the absolute convergence. So now this is step number 2. Does it converge without absolute value?
Without absolute value converges, yeah.
Yeah, because?
With the alternating series test.
Exactly, absolutely correct. So this one, that's alternating. Absolutely, that's the only thing we know what to do with. The terms go to 0. You guys have to basically verify yourself. So those terms equal to 0. You can divide by K squared both sides. And this will eventually, this sequence is decreasing. And I told you this is not obvious why it decreases, because numerator increase and denominator. But for those you sketch the function, because this function is decreasing. That's the only way we can check it's decreasing. Okay, so by the alternating series test, the series converge. Hence, conditionally convergence. All right. Any other questions? All right. So today what we are going to do is the following. Let's see what we have so far. So far we've studied a bunch of tests. Okay. We studied the divergence test, which tell me if the terms don't go to 0. Okay, we're done. Alternating series test is it works, but only for very specific series. So the alternating series test is not a general test. It only works when series go plus minus, plus minus, plus minus. They are alternating. And we will encounter a lot of alternating series next chapters. That's why they are important. So they alternate. So they are very specific type of series. Now for a general series with positive term, only with positive term, we have choices between integral, limit comparison, and comparison. That's really the choices we have. And in the limit comparison and comparison, we always compared with P series or geometry, because that's the only thing we know. But there is an issue. Whether it's limit or comparison, we need a series to compare with. If we don't have it, we don't know what to do. Sometimes it's hard to find a series to compare to. So let me take the following. Suppose I give you the following series. Sigma n squared over 2 to the, The book we were using last year used n. So I'm so used to n. And this year we're using this new book that uses k. So suppose I have this series, sigma k squared over 2 to the k. And the question is, does it converge or diverge? Or diverge, okay? Now, integral test is a nightmare. So I need to compare it. I'm going to use the comparison test. But here is the problem. What shall I compare it with? What shall I compare it with? So it means if k is large, what can I compare it with? Is there anything I can compare this series with? What do you think?
Could you do k squared over 2k plus 1?
But what's the benefit? Do I know we usually compare with something we know its behavior. Means we either compare with a p series, 1 over k to the p, or geometric, r to the k. So even if I do that, what's the benefit?
Nothing.
Exactly. So there is nothing I can compare with. So comparison test in this case get me nowhere. So now we're going to see another test, which is very, very important and easy for the student to use, which doesn't require us to compare the series to anything. So it's a test that will not require to compare it to another series, and the test work for series with positive or negative terms. Okay, and we're going to call it the ratio test. So today we're going to introduce a new test, which is, I think this put me in section 10.7, ratio test. So, and address this issue where there is nothing, I don't know what to compare my series with, but it doesn't compare it to anything at all. So we're going to state the ratio test and then we're going to work with it. So I will state it. Here it is, the ratio test. Let sigma ak, I read it very slowly, be a series. I didn't say positive terms, it's just a series. And let R be the limit as k goes to infinity of the ratio between ak plus 1 and ak. It means ak plus 1 is the term that comes after ak. So let R be the ratio between them. That's where the word ratio test is coming from. Then the ratio test tells me if this ratio is less than 1, basically, because the ratio have to be positive because I'm taking them in absolute value. If the ratio is less than 1, then the series will converge absolutely, hence converges. So if the ratio, I should remind you the geometric series, because the proof is actually based on the geometric series. So if the ratio is less than 1, then the series converge absolutely, hence converges. So the series is fine. If the ratio is bigger than 1, the ratio here, the series will diverge. Absolutely, not absolutely, the series purely diverges. The only problem that this test has is when the ratio is equal to 1. So when the ratio is equal to 1, the test is inconclusive. It means that the series may converge or diverge. Another test should be used. So that's really the ratio test. So it does not require us, as I said, to compare to anything else because it takes the ratio between two consecutive terms and study this ratio. And the ratio less than 1 convergence, larger than 1 divergence, we have issue at this stage. If the ratio happens to be 1, then we have to go back to what we know, whether it's alternating or whether it's limit comparison or integral test, the other stuff. Okay.
Could you show the top of the page again real quick?
Yes. Yeah.
Thank you.
Okay. I'm giving you a minute so that you guys write this down.
So I have a question.
Yes.
So there's no way for a ratio test to just converge. Like it's always going to be absolutely converge. Converges absolutely.
But if it converges absolutely, then
Oh,
it will
then
converge.
it converges. Okay.
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 So if I have a series with positive terms, I mean, if the series have positive term, absolutely or non-absolute, it's the same thing. If they are positive.
Oh, okay, okay.
Right? So if they are
Yeah,
positive,
'cause
even the absolute value doesn't really make sense. Absolute value makes sense when the terms start to become positive, negative, positive, negative. But if the terms are positive, it's the same thing. Right?
Yes. Thank you very much.
Oh, sure, anytime. Any other questions before we proceed and start applying it? Now I'm going to go back to this test, this series, and we're going to see does it converge or diverge. So now we're going to use the ratio test because we're going to practice the ratio test today and to check the conversion. So use ratio test. To decide if the series converge or diverge. Converge or diverge. All right. So the first example, that's my series sigma ak, so k squared over 2 to the k, my k going from 1, let us say, to infinity. Right. So how does the ratio test work? First, we have to say what my ak is in this problem. My AK are the terms, so it's not alternating. So the AK are the terms themselves, k squared over 2k. And as here, the series has positive terms, so absolute, non-absolute, that's all really the same. It doesn't really matter here. Now what's AK plus 1? Immediately we have to say what AK plus 1 is. It means the term that comes after AK. That's really what it is. So AK plus 1 is whatever that is k, I plug in k plus 1. And what is that is k, I plug in k plus 1. Okay, so that's ak plus 1, the term that comes right after ak. So when I'm writing them down here, so that's like a half plus 2 squared over, I mean, it happened to be 2 squared over 2 squared plus 3 squared over 2 cubed. That's really what I am adding. 4 squared over 2 to the power 4, and so on and so forth. So if this is AK, this is AK plus 1. If this is AK, this is AK plus 1. Right? Now I have to look at the ratio. R is the ratio of AK plus 1. I did not need the absolute value here because everything is positive over AK. And now let us compute this ratio. That's the limit. So as you realize, I did not need something else to compare the series with. I compare it within itself, if you want. Of AK plus 1 is k plus 1 squared over 2 to the k plus 1 divided by AK over 2 to the k. All right? And so it looked like a mess, but as you realize, it's not a hard limit. So now, of course, I'm not going to keep it like this. We're going to use the property of fractions to proceed. So it's k plus 1 squared over 2 times 2 to the k over k squared. Okay, now I need to find the limit. Now, an easy way to find those limit is, because they look like hard, is put like term together. So what do I mean by put like term together? Like those two are like terms, so I'm going to put those together times 2 to the k over 2 to the k plus 1. So most of the time we try to do that when we use the ratio test. Now let's see if this is equal to 1. Remember, I need to find the limit. Like in this particular example, I have k plus 1 squared over k squared. I actually can put the whole thing squared, just because it makes the math easy. Times. Now, 2 to the k over 2 to the k plus 1. Can I simplify this expression? And what do I get? Back to you now.
Yeah, you get 1/2.
Exactly, because
It's like 2 to the k plus 1 is the same as 2 times the k.
absolutely correct. 2 to the k over 2 to the k plus 1 is actually 2 to the k over, if you want to split it, 2 to the k times 2, because 2 to the k plus 1 is 2 to the k times 2, which is equal to 1/2. It's not the limit. This is actually exactly equal to 1/2. So this term here is exactly 1/2. Okay? So now it is equal to what finally? When k goes to infinity, k plus 1 over k, this will go to 1. Then this is equal to 1/2. That's r, strictly less than 1. Okay. Now, none of the tests tells me the value of the sum. All the tests just tell me whether it converges or diverges. So the ratio is less than 1. Hence, by the ratio test, the series converge. The series converges. Okay, so that's how the ratio test is applied. Question before I move on. Example number 2. So let's see. Example number 2. Before I do example number 2, I have to, because we're going to start using those a lot, we have to a little bit remind you, let us recall the idea of factorial. Okay, factorial. So let us remember what is a factorial. 0 factorial is by definition 1. 2 factorial, it's 1 times 2. 3 factorial is 1 times 2 times 3. Okay, and then 4 factorial is 1 times 2 times 3 times 4. Okay, so this is an idea which we're gonna start using it quite a bit actually. Then 5 factorial is the same thing, 2, 3, 4, and 5. Okay, so in general, k factorial, if you want, means you keep multiplying the terms 1, 2, 3, all the way to k. Okay, that's what k factorial is. Right. One of the facts that we're going to be using in the ratio test is a relationship between k plus 1 factorial and k factorial. So before I use it in the example, let me make a note. Let us note something. Let me compute, for example, 6 factorial. 6 factorial, actually, let me ask you a question before I do that, so you know what I'm doing. What's the relationship between, if I want to write 5 factorial in terms of 6 factorial in terms of 5 factorial? What's the relationship between them? 5 factorial and 6 factorial.
The 5 factorial times 6.
Right, it's 5 factorial times 6. It's the results that we're gonna be using it quite a bit, because 6 factorial, you keep multiplying all the way up to 6. So 6 factorial is going to be this piece, which is the 5 factorial, times 6, as simple as that. Okay. So in general, we're gonna have the following: k plus 1 factorial. First, this is not, let's get that straight. This is not that. You cannot split a factorial. Okay, you cannot split the factorial. So we have to be very careful with that. When we do working with factorial, you know, we tend to mess up. So we cannot split a factorial. Let me just pick a number. 5 plus 1 factorial, which is 6 factorial, is not 5 factorial plus 1. It's actually 5 factorial times 6. But what's the relationship between k plus 1 factorial and the one before it? What's the relationship between those in general?
Is it k factorial times the quantity k plus 1?
Absolutely correct. Okay, for the same reason as here. So k plus 1 factorial is k factorial all the way times k plus 1. Because in the k plus 1 factorial, you start multiplying times 2 times 3, and you keep multiplying. The last term is k plus 1. It's like in the 6 factorial. But the one before k plus 1 must be k. So this is the k factorial, and this is the k plus 1. Okay. So now we're going to do another example, and we're going to start using factorial a lot at this stage. So let me take the following series: sigma to the power, let us say 2k over k factorial, k equal 1 to infinity. Okay. And the question is, use the ratio test, because none of the other tests can be applicable in this case. I mean, forget it. Use the ratio test to decide whether the series converge or diverge. All right, so the ratio test. We're going to take AK, in this case, is 2 to the power 2k over k factorial. Then immediately we say, what's the term that comes after? K plus 1 is equal to what? All right, instead of k here, watch, I'm putting parentheses, is to k plus 1. So we have to be very careful with what we're doing. What about the numerator? What it will become? What will the numerator become? Back to you.
Going to be 2 to the power of 2 times k plus 1.
How do you want me to write k plus 1?
Parentheses.
Exactly. Be very careful. Be very careful with everything you do. All right. Now I have to take the limit of the ratio. So that's R is the limit as k goes to infinity of the ratio between ak plus 1. As you realize, in this problem, I did not take the absolute value because the terms are positive. Otherwise, I will have to take the absolute value. But all the terms are positive, so that's why I dropped them. So you guys can write this as a note for yourself. So this is the limit as k goes to infinity of the following. All right. 2k plus 1 over the quantity k plus 1 factorial, the whole thing divided by 2 to the 2k over k factorial. And now I have to use property of fraction. I have to over k plus 1 factorial times that over 2 to the 2k. So finally, this is equal to, as I said in the previous problem, just to make it a little bit simple for us, little bit simple, I like to put the like term together, or basically under each other. So those two, I put them together. Now, 2 times k plus 1 is basically 2k plus 2 over 2 to the dk times k factorial over k plus 1. Right? So now before I jump into finding the limit, I will simplify those terms, because we know a lot of simplification can occur. So you don't just jump to the limit, we just simplify. So let's see what we have in here. 2 to the k plus 2 and 2 to the k. Now, obviously, it's, I can write it this way to make things easy for us, times k factorial. Now, the quantity k plus 1 factorial, because we know we need to simplify, as I mentioned a minute ago, that's k factorial times the k plus 1. So that's why we mentioned that. So we write this here again. So k plus 1 factorial is all the terms, you multiply them up to k times the last term, which is the k plus 1. And finally, it's going to be simple. This go away. K factorial go away. So what I'm left with is the following. 4 over k plus 1. That's what I'm left with. But as k goes to, this is equal to 0. Now the ratio test tells me if the limit is 0, this is strictly less than 1. By the ratio test, the series converges. Okay, so by the ratio test, the series will converge. Okay, so it's not a hard test to use. It's a very powerful test. We will use it a lot. So the series will converge by the ratio test. All right, now let's take one more example. Let me take the following problem. Okay. Sigma sigma 1 over n squared plus n from 1 to infinity. Okay, and before I start this problem, I'm going to ask you a question. If you were faced with this series, what do you think is the best test to use? Back to you. Remember, you have really a lot of them by now. If you're faced with this series, what do you think the best test to use?
The comparison test,
Exactly. Which one you want?
1 over n squared.
Exactly. That's the limit comparison, right? So you compare it with 1 over n squared. Absolutely. If I am doing it, I immediately look at the limit comparison test, and then I will deduce. Let us say, for the sake of thing, let us use the ratio test. And let's see what happens. So we're going to use the ratio test. Okay, now let's see what happened in this scenario. And I always write n because I cannot get over this habit easily. K squared plus k. All right, let's use the ratio test. So in the ratio test, this is my AK is 1 over k squared plus 1. And AK plus 1 is 1 over the quantity plus k plus 1. All right, so now let us compute the ratio of AK plus 1 over AK. So that's the limit as k goes to infinity. Again, those are positive. So even if I put the absolute value, it doesn't really matter. And this will be 1 over the quantity k plus 1 squared plus k plus 1 over 1 over k squared plus k. So it's a mess, but we will get out of it. Now this is going to give me k squared plus k. And here I will have plus k plus 1. Okay. Now we need to compute this limit. And the easiest way is this is infinity over infinity, that's for sure. So there are several ways of doing this. You can use L'Hopital's rule. That's, of course, one way to do it. Or we can, I can distribute the denominator. So it will give me k squared plus 2k plus 1 plus k plus 1. So if we distribute, it will become much easier. And this will give me the limit of k squared plus k over k squared plus 3k plus 2. So it's going to be the limit in this scenario.
1.
Yeah. Divide by k squared, which is equal to 1. What does this mean?
Inconclusive.
Absolutely. So the ratio test is a very, very nice test, but it has a problem. The problem is if the ratio happened to be 1, so the test is inconclusive. So the ratio test here is absolutely inconclusive. And tomorrow we will actually discuss when to use each test, some guidelines, of course. So the ratio test is absolutely inconclusive. It means we have to use another test. So in key, it means that in this scenario, we have to use another test. So one test, we have to use another test. And in this case, a good test would be, is the limit comparison test with, we use the limit comparison with sigma 1 over n squared. All right, and the series will actually converge in this scenario. All right, so the ratio test is a very powerful test, but it has also its limitation. Limitation occur when the ratio is 1, and that's where another test is in order. Okay. All right, so that's it for today. As usual, those who have questions, please stay, ask any question you want. For the rest of the class, it is dismissed. Your homework is on Brightspace.